In this question, we're going to graph the curve y equals x squared minus 4x plus 7 over x minus 3. Well, we can start by looking for intercepts. When x equals 0, y is equal to negative 7 over 3. And y equaling 0 is impossible. And the reason for that is because x squared minus 4x plus 7 cannot equal 0. Plug it into the quadratic equation and try it for yourself. It just won't happen. So we see that we have a y-intercept of 0, negative 7/3, and no x-intercepts at all. Now, in terms of asymptotes, we have degree 2 over degree 1, so there's no horizontal asymptote. We have a vertical asymptote at x equals 3, because that makes the denominator 0 and not the numerator. We can't simplify that numerator at all. We can't factor it, so we have degree 2 over degree 1 after simplifying, meaning we have an oblique asymptote. Using long division, dividing x minus 3 into x squared minus 4x plus 7, we see that we get x minus 1 plus 4 over x minus 3. This becomes our result. And because of that, this is our oblique asymptote. Our oblique asymptote is the portion without the remainder in it. So y equals x minus 1 is an oblique asymptote. Now, one thing we can do, one analysis that you sometimes see people do, is they'll say, okay, this 4 over x minus 3, as I go to the far left on the graph, 4 over x minus 3 will be a negative number. As I go to the far left, 4 over x minus 3 is negative. Think of a number like 100 for x. 4 over 100 minus 3 is negative, meaning that our y value will be the value of the oblique asymptote minus something. So that means that we'll be approaching the curve from below to the left. And similarly, as x goes to infinity, 4 over x minus 3 is greater than 0. Think of a number like 100. Plug that in and you'll get a number greater than 0. Well, that would mean that our y value is equal to the oblique asymptote value plus a quantity, which means that we're approaching the oblique asymptote from above to the right. Now, not everyone does this analysis, because if you do the rest of the question correctly, you'll come up with a good looking curve. Okay? Well, we see that we have y equaling x squared minus 4x plus 7 over x minus 3. Using the quotient rule and finding the derivative, it simplifies to x squared minus 6x plus 5 over x minus 3 quantity squared. Our numerator can factor to x minus 5 times x minus 1, and our denominator is x minus 3 quantity squared. That means that y prime is undefined at x equaling 3. At x equals 3, y prime is undefined, and y prime will be 0 when x is 5 or x is 1. So we should figure out y values when x is 5 or x is 1. At x is 1, y is negative 2. And at x is 5, y is 6. Obviously, we're putting those x values into the original expression for y. Okay? Now, our first derivative is given by this expression. Using the quotient rule again, we can come up with the second derivative. Now notice that this quantity has 2 factors of x minus 3, and this quantity has 1 factor of x minus 3. We can common factor that out, and we have x minus 3 on the outside times this whole long factor. In other words, factoring x minus 3 out of here will leave us with x minus 3 times 2x minus 6, and factoring x minus 3 out of here will leave us with this trinomial times 2. Okay? Well, we can cross out this x minus 3 with one of the 4x minus 3's I have down below, so it's gone from the numerator and I only have 3 more remaining in the denominator. Expanding this out, I get this long expression, which actually, believe it or not, simplifies to 8. So we have 8 over x minus 3 quantity cubed. Well, y prime prime will definitely be undefined when x equals 3, and that's no surprise because there's no point there. But there's a vertical asymptote, but y prime prime we can also say will never equal 0. So now we're going to try our interval testing. Y prime is x minus 1 times x minus 5 over x minus 3 squared. Y prime prime is 8 over x minus 3 cubed. Taking a number to the left of 1 and plugging it into the expression for y prime, we'll get a positive number. Taking a number in between 1 and 3 and plugging it in here, we'll get a negative number. if I let x be between 3 and 5, we'll get a negative value for y prime. And finally, a number greater than 5 for x will result in a positive y prime value. Looking at y prime prime, if I let x be a number less than 3, this is a negative quantity, and if I let x be a number greater than 3, this is a positive quantity. So looking at this, we see that we already knew the point on the curve was 1, negative 2. We showed that in the last page. So we see that we're increasing to 1, negative 2 and decreasing after. That means there's a maximum point there. Or alternatively, we can say we've got a slope of 0 at x equals 1 within a concave down region, and that is obviously going to be a maximum point. And we have a minimum point at 5, 6 because we're decreasing and then increasing. Or similarly, we can say we have a horizontal tangent in a concave up region. So we have a maximum point at 5, 6. So putting all of that together, we see we have an oblique asymptote and a vertical asymptote. We know our y-intercept and our maximum and minimum points, and we have these to guide us. And so we have this. This is the point 1, negative 2, and this is the point 5, 6. And this is our y-intercept, 0, negative 7/3. So we can see that in between 3 and 5, we're decreasing, and then we're increasing, and the whole time we're concave up. And I see that I can actually draw that pretty nicely and respect the asymptotes at the same time. This is a curve that's decreasing to x equals 3 and increasing afterwards, and is concave up the whole time because the curve is above any tangent line I could draw. Looking at this one, I'm going to draw a very similar looking curve, basically the mirror reflection of the part on top. And now looking at what we have here, we can see that I'm going to be increasing to x equals 1 and decreasing after and concave down the whole time. And this is what our curve looks like.